The Hifisonix ax-Amplifier, which I'll just refer to as the ax-Amp from here on in, was published in 2024 in April and May in the US-based audio industry magazine audioXpress. This is the third current feedback Class A amplifier I've designed and built, the previous two being the 15-watt SX amp back in 2012 and an updated and significantly refined version of that, the KX2 amp, in 2019, both of which you can read about on the Hifisonix website. This amp uses my tried and tested CFA topology. You will note as we go into the details the front end bears more than a passing resemblance to the SX and KX2 amplifiers, and that's because dozens of those amps have been built. Combined board sales for both those and the Class AB NX amp, which uses the same front end, is 450 since 2012. And other than the odd problems during construction that required a bit of tech support from my side, have gone on to prove reliable amps for their builders. This amp produces 70 watts RMS in Class A at 3.5 ppm distortion. That's 140 watts peak Class A per channel at 1 kHz into 8 ohms. The amp will support peak load currents of up to 26 amps and will drive highly capacitive loads. It uses a technique I've dubbed AFEC, or Augmented Feedback Error Correction, to achieve ultra-low distortion and very high power supply rejection ratios. This is a big amp, weighing in at about 24 kilograms or 50 pounds, and uses a DIY Audio 5U Deluxe chassis, so the PCB and power transistor mounting holes on the heatsinks are all pre-drilled, saving hours of work for anyone building the amp. The amplifier can be switched between Class A, Class AAB, or Class AB mode. The power dissipation for both channels in full Class A is around 350 watts on plus minus 40 volt supply rails. A plateau bias circuit switches the amp to Class AB mode if no music is detected for about 40 seconds in Class A, saving around 280 watts in power dissipation. Despite the very low distortion, I'd characterize this amplifier as sounding warm with a very delicate top end with first-class imaging. The hefty output stage and low output impedance also mean it will deliver plenty of low-end grunt when required. I mostly listen to classical and jazz music on my BMW 703s, KEF LS50s and Dali Oberons. However, given the power on tap, this amp also works very well with modern rock music on the BMW 703s. This block diagram shows the basic operation of AFEC. A1 is a high-power transitional Miller-compensated current feedback amplifier. A2 is half of an ultra-low distortion OPA 1642 dual JFET input op-amp from TI, which is used here as a balanced to single-ended amplifier buffer. The other half of this op-amp is used as the AFEC amplifier A3. The power amplifier A1 feedback resistors are R38 and R37, and in conjunction with the balanced input amplifier set the overall gain to 32 dB or 39 times. The junction of these resistors, point A, feeds into the low impedance inverting input of the power amplifier. With AFEC, a second set of feedback resistors, made up of R4, R11, R8 and R12, tap off the power amplifier output and are set to the same gain ratio as the main feedback resistor pair. The reference signal for the AFEC amplifier is also the input signal to the power amplifier as derived from the output of A2. AFEC amplifier A3 compares the reference signal to point B, extracting from the power amplifier output any residual closed-loop distortion as an error voltage at point C. This error voltage is then converted into an error current by R10 in parallel with R83, which is about 135 ohms, and injected into the main CFA low impedance inverting summing node at A along with the primary feedback signal. The AFEC amplifier is compensated with R13 and C4 and was optimized in LT Spice to ensure no overshoot on square wave input and checked on the 3 prototype builds during development. The main amplifier loop gain is a shade under 60 dB, that's the teal trace, and uses transitional Miller compensation or TMC, as already mentioned, to achieve very respectable distortion of about 35 to 40 ppm at full power. AFEC, which is the red trace, raises the loop gain to a bit over 100 dB. With AFEC engaged, the distortion into 8 ohms drops to around 3.5 ppm. Most of the measured figure, by the way, coming from the audio analyzer where the generated distortion is spec'd at minus 108 dB. Without AFEC, the distortion into 2 ohms is 145 ppm, still a very respectable figure given that this is around 220 watts output. With AFEC engaged, the distortion at this level drops to around 12.5 ppm and is a good demonstration of just how effective AFEC is in this regard. The power supply rejection ratio and IMD are also significantly improved. In Class A, there is a 23 dB improvement in full power IMD from minus 95 dB in Class AB without AFEC to minus 118 dB in Class A with AFEC. The noise floor of the amplifier, reference 60 watts RMS output, is minus 126 dBr. These two scope plots show the performance of the amplifier into capacitive loads. In both cases, the teal trace, which is the right channel, is the amplifier driving just a resistive load and so forms the reference, while the left channel yellow trace shows the amplifier driving the resistive load plus a parallel capacitance. In both cases, the amplifier remains stable with clean recovery and minimal overshoot. In the 3 prototype builds, stability into a range of capacitive loads from 1 nanofarad up to 2.2 microfarads in parallel with 2 ohms up to 8 ohms and open circuit load resistance was checked. The amplifier will remain stable with any load combination of 2 ohms and higher in parallel with any capacitive load of up to 2.2 microfarad, which were the test limits that I used. This is the front-end circuit diagram. I won't go into the circuit details component by component since this is done in the audioXpress articles you can download for free on their website. I've put the link to the articles in the comments section below. The green shaded area is the AFEC amplifier, which we've just discussed a little earlier. Note that the ax-Amp only accepts balanced signal inputs, and you cannot use a balanced to single-ended adapter cable with this amp. You have to provide it with a fully balanced input signal. This is the output in TIS, also called voltage amplifier or VAS by some designers. The key points here are the amplifier uses a simple EF2 output stage and 4 pairs of 200 watt sustained beta transistors, NJW3281 and NJW1302 devices. I did this because this is a Class A amp and the standing dissipation is high. It is important to avoid thermally stressing the output devices, and this approach means the heat dissipation can be conveniently spread out across the heatsink. With long-term sustained Class A operation, the heat sinks run at about 55 Celsius, with ambient at around 25 Celsius. As already mentioned, the amplifier will deliver up to 26 amps into the load, so it is very capable of driving difficult loads. The voltages highlighted in red on the schematics are the voltages you would read with your meter on an operationally perfect amplifier with the input shorted and an 8 ohm load, and makes for very easy debugging. The area highlighted in green is the plateau bias circuit. J6 is connected to a miniature on-off-on toggle switch located under the amplifier just behind the front panel and allows it to be switched between Class A, Class AAB and Class AB. If set to Class A, the amplifier output stage standing current is 2.2 amps per channel, 1.1 amps if set to Class AAB, and 400 milliamps in Class AB. Details on operation are given in the audioXpress article. The output stage current is directly regulated by a simple 2-transistor controller, Q1 and Q2, which are BC847 SMD devices, and this graph shows the regulation performance from ambient to full operating temperature. The heatsink temperature goes from 25 Celsius to about 57 Celsius in around 30 minutes, but the standing current changes by less than 1.5% from 5 minutes after power up to the full operating temperature. Note that for this test I had to drive the amplifier so that it remained in Class A, since without any input stimulus, the amplifier will revert after 40 seconds back to Class AB operation in order to save power. This plot, generated using a QA401, shows the ax-Amplifier output impedance and the effect of the output coupling inductor L1. My implementation used a Hifisonix speaker protection board with circa 15 milliohm end-to-end switch resistance. So from the measured output impedance, which is a red trace, subtract 15 milliohms and the black dashed line is the result, which indicates that the output impedance of the ax-Amplifier is below 20 milliohms. The dots on the right-hand side show the calculated effect of the output inductor, and that's why the output impedance rises in the upper part of the audio range. This increase in output impedance at HF isolates any capacitive load from the amplifier at high frequencies, ensuring the amplifier doesn't suffer from HF output pole migration, leading to excessive loop gain phase shifts. If you want to build this amp, you can get a set of double-sided throw-plated silk-screened gold-flashed PCBs at the Hifisonix shop. Links are in the comment section below. For $48 plus $15 shipping. Power supply, PCB, speaker protection PCB, and soft start PCBs are also available at the Hifisonix web shop. And if you want to build the amp exactly as the original, a PCB bundle with all the boards is also available. There's a thread about the AX amp on DIYaudio.com in the solid state forum where you can get helpful advice if you run into any problems during your build. However, I'm always available to help as well. Just email me at ponsai@hifisonix.com or visit the hifisonix.com website and post your questions up in the comments section. Don't forget to visit audioXpress. There you can download the two-part article, the BOM, detailed assembly instructions and test instructions, additional measurement, and other supplementary material. The links are below in the comments section. That's it. Trust you liked the video, and if you did, feel free to share the link and give it a thumbs up. Thank you.